Now here is our next question, number 21. The Nyquist plot of loop transfer function g of s into h of s of a closed loop control system passes through the point of -1, j0 in the g of s, h of s plane. The phase margin of the system is 0, 45, 90, 180 degrees. Okay. So here, since we are supposed to find out the phase margin of the system, we have a direct formula. Now the phase margin is phi. Okay. And the formula for this is g of j omega times h of j omega at omega equals omega 1 plus 180 degrees. So the phase margin is g of j omega, h of j omega plus 180 degrees. Now, since we already have the angle here, we will have to find out what this expression is in terms of the point of -1, j0. Now, at -1, j0 at this particular point, g of j omega and h of j omega is -180 because here we have a -1, right? -1. So -1 in the g of s and h of s plane is -180 plus 180 in the formula over here. So what does that give us? Phi is 0 degrees. So option A is the right answer in this case. Okay, here's the next question, number 22. Consider the function f of s is equal to 5 divided by s into s square plus 3s plus 2, where f of s is the Laplace transform of the function f of t. The initial value of f of t is equal to, so we have our four options, 5, 5 by 2, 5 by 3 and 0. Okay. Now because the question says initial value, that immediately should give us a clue. We are supposed to use the fundamental concept of initial value theorem. Okay. Now, according to the initial value theorem, the initial value of f of t is equal to the limit of s tends to infinity, s times f of s. So this is what we are supposed to find, right? So the initial value of f of t is equal to the limit of s tends to infinity, s into f of s. Now according to the question, we have been given that f of s is this expression. So substitute this value over here. What do we get? 5 divided by s into s square plus 3s plus 2. We can cancel out the s over here, right? And that leaves us with limit of s tends to infinity, 5 divided by s square plus 3s plus 2. So if we substitute the expression of infinity in this case, so limit of s tends to infinity, 5 divided by s square plus 3s plus 2. Now, infinity, if we add over here, anyway, 5 divided by such a large number is obviously 0. So, our final answer is D, 0. Here's the next question, number 23. For a tachometer, if theta of t is the rotor displacement, in radians, that's in, okay, E of t is the output voltage and kt is the tachometer constant in volts per radian per second. Then the transfer function of E of s by theta of s will be given as, okay, so this is theta of s, if that isn't clear. Okay, so I hope everything is clear so far. Now the given options are kt into s square, kt by s, kt into s and kt. Now this is of course in terms of Laplace transform or s domain. Now for a tachometer, the first thing we will have to do is write down the voltage equation. So the voltage equation, over here we have been given that the output voltage is E of t. So E of t is given as the tachometer constant kT into d theta by dt. Okay? So this is in time domain. Now if we are to convert this into S domain, what happens? Now here we have E of t will become E of S. The constant kT d theta by dt can be written as S into kT into theta of S. Now the transfer function is in terms of E of S by theta of S. So this can be further written as E of S divided by, now I am going to bring this down, theta of S. What is left out? S into kT. Now check, where does this option come under? It comes under option C. So kT into S is the final answer here for the transfer function of the tachometer. Here's the next question, number 28. The circuit in the figure shows a full wave rectifier. The input voltage is 230 volts RMS single phase AC. The peak reverse voltage across the diodes D1 and D2 is. Now the four options say 100 root 2, B gives 100 volts, C is 50 root 2 and D is 50 volts. Now in order to solve this problem, we first have to understand what the peak reverse voltage is. The peak reverse voltage. Now the peak reverse voltage, also known as the peak inverse voltage or PIV, is the maximum possible voltage across a diode. So this actually happens when it is in reverse bias. So it is the maximum possible voltage across a diode in reverse bias. So if you notice the diagram over here, we have our primary and secondary. You will see that the full wave rectifier here, the rating has been described over here, 230 volts by 50, 0, 50 volts, center tap, right? So during the first half cycle of the supply, the top of the transformer secondary winding is positive. So what happens is the diode D1 starts to conduct. It is in forward bias. So this provides almost zero resistance because it is in forward bias. The entire voltage of the upper half winding is developed across this load here. Let's call this RL. Okay. So now the voltage across the non-conducting diode D2, this is in reverse bias. So PIV is the maximum voltage across the non-conducting diode in reverse bias. So in reverse bias, what happens is the voltage here, the voltage at D2 is the sum of the voltage across, sum of the voltage, the sum of the voltage across the non-conducting diode D2, the sum of the voltage across the transformer secondary and the voltage across the load resistance RL. Across the load RL. So what this actually means is that PIV of D1 and D2, they will both be the same because at one half cycle, D1 is in forward bias while D2 is reverse bias, and then in the next half cycle they interchange that way. So PIV would be the sum of the voltage across the transformer secondary, which is VM, maximum voltage, plus the voltage across the load RL would be VM again. So PIV is equal to 2VM. Let me just grab another sheet of paper and we'll continue to the next step. So far we have PIV of D1 is equal to the PIV of D2, which is equal to 2Vm, right? Okay, so in the question over here, we have been given the RMS value, 230 volts RMS is given. So in order to find the peak value, we know the formula that V peak or Vm is equal to V RMS times root 2. This is the formula. So if we have to write the PIV in terms of V RMS, what happens over here? We get 2Vm becomes 2 into V RMS times root 2. Now, according to the diagram over here, notice that what is the voltage across the secondary? It is 50 volts, right? So 50 volts is the V RMS. Now let's substitute that over here. What happens? Let's see, that's 2 times 50 root 2, which is 100 root 2 volts. So the answer over here is 100 root 2 volts, and that matches with option A. So this is the solution, and I hope it has helped. Here's the next question, number 29. The triggering circuit of a thyristor is shown in the figure. The thyristor requires a gate current of 10 milliamps for guaranteed turn-on. The value of R required for the thyristor to turn on reliably under all conditions of VB variation is. So take a look at the figure over here. We have VB and the value is given as 12 plus or minus 4 volts. And our 4 options are 10,000 ohms, 1600 ohms, 1200 ohms and 800 ohms. Okay, so let's take a look at how we can solve this. Now first, let's write down the maximum variation of VB over here. So that's VB max. I'll write it down here. VB max. Now VB max is equal to, so that's 12 plus or minus 4 volts, right? So minimum would be 8, maximum would be 16. So this is 16 volts. VB is 16 volts, 12 plus 4. Now the next step is to write down the formula for the resistance. Now we are quite familiar with the basic Ohm's law, right? We know that R is equal to V by I. Now V is VB max. And I here is the current or the gate current that is given in the question, the thyristor gate current. So that's I gate. So what do we have the values over here as 16 divided by, now what is the gate current given? 10 milliamps. So that's 10 into 10 power minus 3. Now solving this gives us a value of 1600 ohms, which matches option B. So for this question, the answer is 1600 ohms. Here's the next question, number 30. The circuit shows a 3-phase half-wave rectifier. The source is a symmetrical 3-phase 4-wire system. The line-to-line voltage of the source is 100 volts. The supply frequency is 400 Hz. The ripple frequency at the output is. So here we have 3-phase half-wave rectifier given to us, and it's a 4-wire system. And the supply frequency is given to us as 400 Hz. Now, you are quite familiar with the fact that for a half-wave rectifier, when it conducts, the output is just half of every cycle, isn't it? So if we have our input here, let's consider one cycle of the input. This is a single phase, okay? So what happens at the output? At the output of the half-wave rectifier, for every cycle we will receive only half of the input. based on the arrangement of the circuit, it can be either the top half of or the bottom half. So these pulses that we get over here as the output of the waveform, the series of these pulses is at a frequency that is equal to the same frequency of the input. So this is actually known as the ripple frequency. So usually for a single phase, the ripple frequency is the same as the output. Now if the supply frequency is say 400 Hz for a single phase input, then for the output the ripple frequency will also be the same as 400 Hz. But what do we have here? We have a three-phase system. This is a three-phase half-wave rectifier. So for a three-phase, what happens is, let me write that down. For single phase, supply frequency is equal to ripple frequency. But for three-phase, ripple frequency is 3 times the supply frequency. So that tells us that if the supply frequency is 400 Hz, then the ripple frequency would be 3 times 400. So here 3 times 400, which is 1200 Hz. So the answer over here is C, 1200. Here is the next question, number 31. The RMS value of the periodic waveform given is, so we have our 4 options, 2 root 6, 6 root 2, root of 4 by 3 and 1.5. Now what we have to remember is that the RMS of the waveform is equal to the RMS of one period of the function. So here we will have to just take a note of the period from 0 to t. This is one period, one cycle of the waveform. So to find the RMS value of the entire waveform, we can just find out what is the RMS value of one period. That would be the same as the RMS value of the entire waveform. Okay? So you will have to note the basic formula for the RMS of any waveform. So let's write that down. The RMS value for any waveform is 1 by t 0 to t f square of t dt whole under root. I hope that is clear. So this is the RMS value for any waveform. We will have to first here find out the function f of t. Now we have the entire time period as 0 to t. So 0 to t and 1 by t is the same for this problem. But we now have to find out the function of f of t. Now in order to do that, we have to look at this waveform. Now from 0 to t by 2, we have a linear line, correct? And from t by 2 to t, we have a straight line at 6. So from t by 2 to t, we have a constant value of 6. But from 0 to t by 2, we have a linear line. Now because we have this slope here, we have to go back to our basic about writing down the equation of a straight line and then solve. So let me just grab another sheet of paper and we'll begin. Okay, now let me first write down the same formula. Formula for RMS value, which is 1 by t root of 0 to t f square of t dt. Okay, now let's take a closer look at the diagram, the waveform given. So first we have a slope here and then a constant here. Now this point is our origin 0. Here we have, this is minus 6, this is positive 6, and here this is t by 2 and t. Now consider just from 0 to t by 2 portion, this portion here. if this is the origin, so we know the point here 0, 0. Now what is the point over here? At this point it is t by 2, minus 6. Right? Okay. Now using this we are going to find out the slope of this line. So that is our next step. Let's find out the slope. Do you remember the formula of the slope? M is equal to y2 minus y1 divided by x2 minus x1. Now let's substitute the values over here. What is y2? Consider this to be a point x2, y2, and this is x1, y1. So here we would have minus 6 minus 0 divided by t by 2 minus 0. And that gives us a value of minus 12 by t. So here the slope m is minus 12 by t. Now what is the equation of a straight line? Equation of a straight line is given by y is equal to mx plus b or c. Now here, because the line passes through the origin, b is anyway 0. So we'd have y is equal to mx. So m is minus 12 by t, and what is x? X is t, because here the axis is t-axis. It is time domain. So here the equation of the circle in our problem, we will consider it to be y is equal to, So y is equal to m is minus 12 by t into t. Or we can just simply write this as minus 12t by t. So this is going to be the equation for our slope here from 0 to t by 2. And from t by 2 to t, the function is a constant, which is 6, because it is a straight line. Okay, let me just grab another sheet of paper and we'll write it down. So now our RMS value is 1 by t will remain the same. We are going to split the integral into two parts. Okay, so first we will write down 0 to t by 2. And what is the function of 0 to t by 2? Minus 12t by capital T square dt. Because it is s square of t, right? So this is our first part of the function. Next, plus integral t by 2 to t, that is the next thing. And we have our constant of 6. So that's 6 square dt. And the whole thing is under root. Right. There. Okay. Now let's solve this. So first, let's take care of the parts over here. Now what will we have here? We'll have 1 by t integral 0 to t by 2. That's 144t square by capital T square dt plus integral t by 2 to t 36 dt. And right. Okay. Next. Okay, next. Let's solve this further. So if we take 1 by t inside, we will now have 0 to t by 2, 144t square by capital T cube dt plus, let's take the constant outside for this part, t by 2 to t, 1 by t dt. The whole thing to the power of 1 by 2. Anyway, here t is also a constant. We can actually bring that out over here. Anyway, so now for the next step, let me just squeeze that in here. Let's integrate. Now when we integrate, what do we get? We will have 144 by t cube times t cubed by 3 at 0 to t by 2 plus 36 by t from t by 2 to t. I hope this makes sense. 144 by t cube is the constant here. Integral of t square is t cube by 3 at the limits of 0 to t by 2. And then plus we have 36 by t as the constant. Integral of 1 is t at t by 2 to t. So this is our statement. Now let's solve this further by applying the limits. Okay, so we will now have 144 by 3 times 8 plus 32 by 2 under root. So what we have in the previous step over here, we just substitute and then t's cancel out really. So I'll leave that step to you. You can, I'll let you work on that. Here we have 144 by 3 times 8 plus 32 by 2. When we solve that further, we will have 6 plus 18, which further comes to 24, root of 24, and that gives us a value of 2 root 6 amps. So in this case, our final answer is 2 root 6. And let's see which option that matches with. 2 root 6 matches with option A. Well, this is the final answer, and I hope the explanation has helped. Here is the next question, number 32. In the figure, the value of the source voltage is. So we will have to find out the value here of, let's call this E. We have to find the value of E. So our options are 12, 24, 30 and 44. So to solve this, let's consider applying KVL to both these loops over here. We'll call this as loop 1 and we'll call this as loop 2. Now to find out the value of E, the current has already been given here as 2 amps. This is the current that is passing through this branch here. So we don't have to consider this part at all, though we would have to consider the value of current here while considering this branch here. So let's now apply KVL to loop 2. Okay, so we start with the source. E is equal to 6 times 2, that is the voltage across this resistor here, 6 times 2, and then plus 6 times, here we have two currents passing through this branch here. The first current is 2 amps which is passing through here, and the second is 1 amp which is also passing through the same direction. Here we have 1 amp and here we have 2 amps, both passing through this branch and in the same direction. So here it would be 1 plus 2. This is our expression. Now let's solve 12 plus 18, which gives us a value of 30 volts. And that matches option C. Here is the next question, number 33. In the figure, RA, RB, RC are 20 ohms, 10 ohms and 10 ohms respectively. The resistances R1, R2 and R3 in ohms of an equivalent star connection are. So we have our 4 options. Here. So let's first begin by writing down what's given to us. So we have the values given as 20, 10 and 10. So that's RA equals 20 ohms, RB equals 10 ohms, and RC equals 10 ohms. So here we are just transforming the delta to star connection. So we have standard formulas to calculate and find out the values of R1, R2 and R3. So let's use them over here and solve. Okay, we'll start with R1. Now R1 is equal to RB RC divided by RA plus RB plus RC. Now if we solve, and let's plug in the values. That's 10 times 10 divided by 20 plus 10 plus 10. And that gives us a value of 2.5 ohms. So 2.5 is the value of R. Now let's find out the value of R2. Similarly, the formula for R2 would be RA RC divided by RA plus RB plus RC. Let's substitute the values. That's 20 times 10 divided by 20 plus 10 plus 10. And this gives us a value of 5 ohms. Next, R3. R3 would be RA times RB divided by RA plus RB plus RC. And that gives us 20 times 10 divided by 20 plus 10 plus 10, which is 5 ohms. So here our final answers would be 2.5 ohms for R1, 5 for R2, and 5 for R3. So these formulas are important. Now this is to find out the equivalent values of the star resistances when delta resistances are given to us. There. So now our answer would be 2.55 and 5, which matches with option A. So this is the final answer, and I hope it has helped. Here's the next question, number 34. In the figure, the admittance values of the elements in Siemens are YR, which is 0.5 plus J0, Y1 is 0 minus J1.5, YC is 0 plus J0.3 respectively. The value of I as a phasor when the voltage E across the elements is 10 angle 0 volts is. Okay, so here we have our elements, our three elements: resistor, inductor and capacitor. I believe this is an L, YL. And here we have I. Okay, so YR, YL and YC has been given to us. The three elements are connected in parallel. We also have our voltage E given as 10 angle 0. So first let's convert all these three values given, YR, YL and YC, in terms of polar coordinates. I'll write that down here. So we have YR as 0.5 plus J0, and that would be 0.5 angle 0. Next we have YL, which is 0 minus J1.5, and that's 1.5 angle minus 90. And then we have YC. YC is 0 plus J0.3, and that's 0.3 angle 90 degrees. Okay, so these are our values. Now we will use these polar coordinates in order to solve. Now here we have our current from the source, which is passing through each of the three branches. Now let's call the current that goes through YR as IR. And the current that passes through this element over here to be IL. And the current that passes through the capacitor to be IC. So now we are going to calculate what the values of IR, IL and IC are. Okay, so let's start by finding out the value of IR. Now the current through the resistance, the expression can be written as the voltage E times the admittance YR, and that would be 10 angle 0 times 0.5 angle 0. Multiplying the two, that gives us 5 angle 0 amps. Next, we calculate the current through the inductor, IL. So IL is E times YL, that's 10 angle 0 times the value of YL we found to be 1.5 angle minus 90. Multiplying the two, we get the value as 15 angle minus 90 amps. Similarly, the next one we calculate for IC. IC is E times YC, that's 10 angle 0 times the value that we found earlier was 0.3 angle 90. Multiplying the two, that gives us 3 angle 90 amps. So we have the value of the three currents. Now to find out the phasor. The phasor current of I is the sum of all these three currents, IR plus IL plus IC. And that would be 5 angle 0 plus 15 angle minus 90 plus 3 angle 90. Now in order to add the three, we would have to convert them into rectangular quadrants again. So let's do that now. Now 5 angle 0 is 5 plus J0 plus 15 angle minus 19 is 0 minus J15 plus 3 angle 90 would be 0 plus J3. I hope this is clear so far. Now we add everything up and this will give us a value of 5 minus J12. Now our options given in the question are in the form of rectangular coordinates. So 5 minus J12, let's see, 5 minus J12 is option D. So here for this question, the final answer is 5 minus J12, option D. Now here's the next question, number 35. In the figure, the value of the resistance R in ohms is, we have our options 10, 20, 30 and 40. Now in order to find the value of R, we need to consider both the loops in this figure. Let's call this loop 1 and we'll call this loop 2. And let's call the current that is passing through the resistor 10 ohms is I. Now we need this because we will have to calculate the current that is passing through this 10 ohm resistor, both the sides. Now this side anyway we have it as 2 amps. We still need to find out what is the current passing through this portion in order to find out the value of R. So let's first apply KVL and find out the expression for this loop here. Apply KVL to loop 1. So we start with the source 100 equals to 10I plus 10 times I minus 2. That's because the current over here is 2 amps. The 2 amps is in one direction while the current I is in the opposite direction. So it is I minus 2. So this is our first equation. So let's just open up the parentheses, the brackets over here and then solve a little further. 10I plus 10I minus 20. So we have 100 is equal to 20I minus 20. Let's solve for I. We will obtain 120 is equal to 20I and therefore what is the value of I over here? I equals 6 amps. Now we'll apply KVL to the next loop. Alright, now applying KVL to loop 2. Now when we do that, what do we get? We get here the expression 10 into, that's 2 minus I. So 2 minus I would be 2 minus 6, which is minus 4, plus R times 2 is equal to 0. Now solving for R, you will find the value of R to be 40 by 2, which is 20 ohms. And this matches option B. So here, for the value of R in this portion of the figure is 20 ohms. Here's the next question, number 36. In the figure, the capacitor initially has a charge of 10 coulomb. The current in the circuit 1 second after the switch S is closed will be. We have our four options: 14.7, 18.5, 40 and 50 amps. Okay. Now, what we will have to do is analyze the circuit, write down an equation according to mesh analysis or using mesh analysis, derive an expression for the current I, and then solve. So first let's write down what is given to us just to make things a little clear of what we have to use. We have been given charge of 10 coulomb. So that's Q is equal to 10. Then we have time given to us as 1 second. This is after the switch S is closed. And we will have to find out the current I. Okay. Now let's begin by writing down the expression, the circuit expression using mesh analysis. Okay. So using mesh analysis, let's write down the expression. So we start with the source 100. Now 100 equals to R times I. Let's call the current that is passing through here as I. Okay. Plus, what is the voltage across the capacitor when charge is given? That would be Q by C. Alright. So we have 100 is equal to Ri plus Q by C. But what is I in terms of time? We know. Let me write this down over here. We know that I is equal to dq by dt. So let's substitute that over here. So this would now become 100 is equal to R times dq by dt plus q by c. Okay. Let me just grab another sheet of paper and we will continue. Okay. Now, what do we have so far? We have 100 is equal to R into dq by dt is equal, plus q by c. Now, we need the charge to be positive. So what I'm going to do is bring R dq by dt to the other side and writing the equation like this. Please check. That's q by c is equal to 100 minus R dq by dt. Now we'll take the common denominator and check what we have here. We have q is equal to 100 c minus rc dq by dt. Now I'm going to take 100 to the other side. Q minus 100C is equal to minus RC dq by dt. Separating the variables and solving, we can now write this as dq divided by q minus 100c is equal to dt, that's minus dt by rc, right? So what I've done is taken q minus 100c here and then rc down, just separating them. You will have dq divided by q minus 100c is equal to minus dt by RC. Alright. Now what we're going to do is integrating both sides. Now on the left side we are going to integrate it from Q0 to Q, because here our variable is Q. So here we integrate from Q0 to Q, and on the right side we integrate it from 0 to T. We'll integrate it from 0 to T, time T. That is from the time the switch has closed to the time given to us, that is 1 second. So anyway, since we are deriving an expression for I, let's keep it as 0 to T now. Okay, so integrating it, let's see what we have now. So when we integrate, integral of 1 divided by Q minus 100C is ln of Q minus 100C, isn't it? From Q0 to Q. And this equals minus T by RC from 0 to T. This is what we have. Oh. Yeah. So that's ln. After integrating, we now have ln of Q minus 100C from Q0 to Q, which equals minus T by RC from 0 to T. Anyway, 0 to T will give us the same expression of minus T by RC. We can do that. Now here let us substitute and write down what we have. We will get ln of Q minus 100C minus ln of Q0 minus 100C is equal to minus T by RC. Log A minus log B, ln of Q minus 100C divided by Q0 minus 100C is equal to minus T by RC. Now, let's take the log on the other side, which now gives us a value of Q minus 100C divided by Q0 minus 100C is equal to e power minus T by RC, right? Now let's take this expression here. We would now have Q minus 100C is equal to Q0 minus 100C times e power minus T by RC. Isn't that right? Okay. Now we are going to differentiate this expression. Let's differentiate. Now differentiating that expression, let me write that down again. Q minus 100C is equal to Q0 minus 100C into e power minus T by RC. RC over here is the expression for tau. So that's Q minus 100C equals this. Okay, so let's differentiate. Okay, so we are differentiating with respect to T. So when we do that here, Q becomes dQ by dt. Constant, which cancels out, and that equals Q0 minus 100C divided by RC, that's negative, right? So negative RC times e power minus T by RC. I hope this is clear as well. Now, this would be 100C minus Q0 divided by RC, taking care of the negative sign over here, times e power minus T by RC. So this is dQ by dt. But we wrote in the beginning that dQ by dt is what? It is the current I. So 100C minus Q0 by RC times e power minus T by RC is the current I. Now let's write down, we'll substitute the values over here. Substituting, what do we get? 100 times, what was given in the figure? It was given as 0.5. 0.5 minus, the initial charge given in the question was 10 coulomb, so that's 10 divided by, what was R? R is 2 ohms. 2 times 0.5. Now solving this, okay, e to the power of minus 1 divided by 2 times 0.5. Now 2 times 0.5 is 1, which makes it e power minus 1. Now solving this entire portion, you will get the value of I. So here the final answer of I is 14.7 amps. You can solve it and check. You should get the value of 14.7 amps. And 14.7 amps matches with the option A. So for this question, the final answer is A, 14.7 amps. I hope it has helped. Here's the next question, number 37. The RMS value of the resultant current in a wire which carries a DC current of 10 amps and a sinusoidal alternating current of peak value 20 amps is. Now, first let's write down the expressions given. We have the value of the DC current, IDC, given as 10 amps. Sinusoidal alternating current of peak value 20 amps. So IAC is now written as 20 sin t because we have to consider the alternating signal given, the sinusoidal alternating current. So 20 sin t is the expression. Now, let's write down the total current. I of t is given as IDC plus IAC. That is the resultant current. So, we add up both of these parts to get the expression. So, our expression would be 10 plus 20 sin t. Now, we have been asked to find out the RMS value. So, to find out the RMS value, we will use the following formula. So, the formula for the RMS value of current would be IRMS is equal to 1 by 2 pi, that is our total time period of t, 1 by 2 pi because it is sinusoidal, right? So, that's 1 by 2 pi, 0 to 2 pi, I of t square dt, and the entire part is under root 1 by 2. So this is our formula for the RMS of a waveform. So IRMS would be 1 by 2 pi, 0 to 2 pi, IT square dt to the power of 1 by 2. Now we have our expression for I of t to be 10 plus 20 sin t. Now we have to square this and substitute. So let's do that in the next step. Now let's substitute the expression for I of t. What do we have here? We have IRMS is equal to 1 by 2 pi integral of 0 to 2 pi. Now I of t is 10 plus 20 sin t whole square dt, the whole under root. Now let's expand this expression 10 plus 20 sin t whole square, okay? So that's our next step. As 1 by 2 pi integral 0 to 2 pi. Let's see now, this is 100 plus 400 sin square t plus 400, and this entire part is under square root. Right. Okay, now let's solve this further. What we are going to do next is to convert the sin square t in terms of cos t. That's our next. Okay, so we now have 1 by 2 pi integral 0 to 2 pi. Okay, so here sin square t can be written as 1 minus cos 2t by 2. So we write it as 100 plus 400 into 1 minus cos 2t by 2 plus 400 sin t. The whole of this expression is under root. Okay, So now 400 into 1 minus cos 2t by 2 is 200 times 1 minus cos 2t. That's our next step. And we now have I RMS is equal to 1 by 2 pi into integral of 0 to 2 pi 100 plus 200 times 1 minus cos t cos 2t plus 400 sin t dt, and the entire thing is under root 1 by 2. Alright, now the next step. Here, when we open up the parenthesis, we have now 200 times 1 200 minus 200 cos 2t. Now because we are looking for the RMS value, we will have to take the peak value of the entire expression. So we are now going to consider this as 1 divided by 2 pi, integral of 0 to 2 pi, 100 plus 200 is 300 dt. 1 by 2. Now the reason we have done this is because cos and sine are trigonometric functions, and that would lead to the reduction of the value by a small percentage. Because we are looking for the peak value, the RMS value requires the constants alone. So we consider only the constants, 100 plus 200 here, which is 300. So 1 by 2 pi integral of 0 to 2 pi, 300 dt to the power of 1 by 2. Now let's further solve this. 1 by 2 pi, 300 t at 0 to 2 pi, and the whole thing under root. So that's 300 divided by 2 pi into 2 pi, isn't it? So that's 300 times 2 pi divided by 2 pi, 1 by 2. So here 2 pi cancels out. We are left with only root 300. So root 300 gives us a value of 17.3 amps. So 17.3 amps is the final answer. And that matches with option B. So here for this question, the final answer is B, 17.3 amps. Here is the next question, number 38. The Z matrix of a two-port network as given by 0.9, 0.2, 0.2, 0.6. The element Y22 of the corresponding Y matrix of the same network is given by. Now we have our four options, 1.2, 0.4, minus 0.4 and 1.8. Now this matrix given to us is a 2 by 2 matrix, and it is the Z matrix. So we have Z equals 0.9, 0.2, 0.2 and 0.6. Now you are quite familiar with the relation between the admittance and the impedance of any element, isn't it? We know that the admittance Y is equal to 1 by Z. Now because we are dealing with matrices over here, 1 by Z can be written as what? Z inverse. So if we find out the inverse of this matrix, that would be our Y matrix. So let's write that down now. We will have to calculate what is the Z inverse. Now the formula for an inverse of matrix is 1 by get Z into adjoint of Z. So let's start by calculating what is Z. Okay. Now Z, det Z is equal to 0.9 times 0.6, determinant, okay? So 0.9 times 0.6 minus 0.2 into 0.2. So solving this, we get a value of 0.5. So we now have that Z is 0.5. Now adjoint of Z. Adjoint of Z is we just have to shift the position of these two terms, the diagonal terms, 0.9 and 0.6, while the 0.2 terms over here will become negative. So let me write that down over here. I'll just grab another sheet of paper and we'll continue. Okay, so now we have determinant of Z is 0.5 and adjoint of Z can be written as, okay, so here we would have 0.6 minus 0.2 minus 0.2 and 0.9. So this implies that now our Y matrix would be the same as inverse of Z, which is 1 divided by 0.5 determinant of Z into 0.6 minus 0.2 minus 0.2 and 0.9. So now let's divide each term by 0.5. That will give us an expression or a matrix of 1.2. Minus 0.2 divided by 0.5 is minus 0.4. Minus 0.2, again we have 0.4, minus 0.4 here, and 0.9 divided by 0.5 is 1.8. Now this is our Y matrix. The question asks us to find out the element of Y22. We are supposed to find out the element Y22. Second row, second column, which is 1.8. So Y22 is 1.8. And this matches with option D. So for this question, the right answer is option D. Now for question number 39. The synchronous speed of a 7-phase harmonic MMF wave of a 3-phase, 8-pole, 50 Hz induction machine is. So we have our 4 options. 107.14 RPM in forward direction, 107.14 RPM in reverse direction, 5250 RPM in forward direction and 5250 RPM in reverse direction. Now the synchronous speed for the 7th harmonic MMF wave would be in forward direction. So that reduces our 4 options to 2. It can either be 107.14 RPM or 5250 RPM, but it is in forward direction. Okay, so now let's write down what is given to us. We have been given 3-phase, 8-pole, 50 Hz. So frequency is 50, number of poles 8. Okay, so first let's write down the relationship between the synchronous speed and the 7-phase harmonic synchronous speed. Okay, so the synchronous speed for the 7th harmonic would be given as ns divided by 7, where ns is the synchronous speed of the machine. Now, let's first find out what ns is. Now, we know the formula for ns. The synchronous speed formula is 120 f by p. Now, we have the values of both frequency and poles. So, let's substitute both of them in this and find out what the value of synchronous speed is. Okay. So let's substitute ns equals 120 into frequency 50 by poles 8. And that gives us a value of 750 RPM. Now, the required speed. Now the required speed would be the synchronous speed divided by 7. That is the synchronous speed for the 7th harmonic. So now for the 7th harmonic, which is ns by 7, that would be 750 divided by 7, which would give us a value of 107.14 rpm. So this is our answer, and this matches with option A. Remember that it is going to be in forward direction, right? So here. So our final answer is A for 107.14 rpm in forward direction. Here's the next question, number 40. A rotating electrical machine having its self-inductances of both the stator and the rotor windings, independent of the rotor position, will be definitely not developed. So what will it not develop? Starting torque, synchronizing torque, hysteresis torque, or reluctance torque? Now, it is given that the two self-inductances, here both the stator and the rotor inductances, they are independent of the rotor position. So what happens over here is, with synchronizing torque, we tend to synchronize the relative rotor position, because it is dependent on rotor position. Amongst everything, synchronizing torque depends on rotor position. Let me write that down over here. What happens is, with synchronizing torque, it tends to synchronize the relative rotor position. And it is because of this that the answer over here is synchronizing torque. Now the question says that it is independent of the rotor position, but over here synchronizing torque tends to sync with the rotor position. That is why because it is independent of the rotor position, it will not develop synchronizing torque. So here B is the right answer. On to the next question, number 41. The armature resistance of a permanent magnet DC motor is 0.8 ohms. At no load, the motor draws 1.5 amps from a supply voltage of 25 volts and runs at 1500 rpm. The efficiency of the motor while it is operating on load at 1500 rpm, drawing a current of 3.5 amps from the same source, will be. So we have to find out the efficiency of the motor here. So let's start by writing down what's given to us. So here we have the armature resistance given as 0.8. Then we have the current drawn as 1.5 amps at no load. So let's call that I1. Okay, so this is 1.5 amps. Supply voltage is given as V equals 25 volts and it runs at speed 1500 rpm. The efficiency of the motor needs to be found when the current drawn is 3.5. So let's call this as I2, 3.5 amps. Now in order to find out the efficiency, we have to calculate power. What type of power? 1, we need the total power, and 2, we need the total losses also, because we know that the efficiency is output to input ratio. Total power minus total losses divided by total power. Now let's calculate each one. We'll start with total loss. So here total loss can be written as constant loss plus variable loss. Now constant loss can further be written as power at no load minus armature loss. So let's write down an expression for the total loss here. So total loss, constant loss. Let's start with power at no load. Now the power at no load can be written as V times I1 minus, what is the armature loss? Armature loss is I1 square RA plus variable loss. Variable loss is I2 square RA. I hope this makes sense so far. Now let's substitute the values for each one of these terms and find out what the total loss is. Okay. So V times I1, that is 25 into 1.5 minus 1.5 square times 0.8 plus I square R, right? So I square R would be 3.5 square, that's I2, into 0.8. Now when you solve this entire portion, you should get a value of 45.5 watts. Now this is our total loss, 45.5 watts. Now let's calculate what the total power is. Let me just grab another sheet of paper. Okay, so now let's calculate the total power. The total power can be given by the expression of the supply voltage V times the current I2. So that would be 25 into 3.5, and that gives us a value of 87.5 watts. Now let's substitute these two parts into the efficiency. Now efficiency in percentage, let's calculate directly. So that would be the total power 87.5 minus the total losses 45.5 divided by total power 87.5 times 100 to give us the efficiency. So the efficiency would be 48%. Now looking into the options, 48% matches with option A. So for this question, the final answer is 48%. Here's the next question, number 45. Two three-phase Y-connected alternators are to be parallel to a set of common bus bars. The armature has a per-phase synchronous reactance of 1.7 ohms and negligible armature resistance. The line voltage of the first machine is adjusted to 3300 volts and that of the second machine is adjusted to 3200 volts. The machine voltages are in phase at the instant they are parallel. Under this condition, the synchronizing current per phase will be, okay. So let's start by writing down what's given to us. We have the synchronous reactance given as 1.7. We have the line voltage of the first machine, line voltage of the second machine. So let's write that down as first synchronous reactance 1.7 ohms. Let's call the line voltage of the first machine as EL1. This is 3300. And let us call the voltage of the second machine, the line voltage of the second machine as EL2, which is 3200. Now because we are to find out the current per phase, first we need the voltage per phase. So let us first calculate E phase for the first machine. That would be 3300 divided by root 3. And over here, the phase voltage for the second machine would be 3200 divided by root 3. Okay. Now we have the phase voltages ready. Let's next calculate the circulating current. The circulating current IC. Now IC is equal to the resultant voltage divided by the impedance, the synchronizing impedance of machine 1 plus the synchronizing impedance of machine 2. Now, the synchronizing impedances is equal to the synchronizing, what did we have there? The synchronizing reactance given to us in the question. So here the voltage, the resultant voltage, the resultant EMF can be written as E phase 1 minus E phase 2 divided by ZS1 plus ZS2. Okay, so let's now substitute the values. E phase 1 minus E phase 2. What did we have over here? We had 3300 minus 3200 divided by root 3 into. Now we have ZS1 plus ZS2. So the synchronizing impedance is the same as the synchronizing reactance given to us, which is 1.7. So 1.7 plus 1.7 over here. Now solving this, let's see, we have 100 divided by root 3 times 3.4. Okay, so calculate this. You should get a value of 16.98 amps. So our circulating current is 16.98. So that is our synchronizing current per phase, 16.98. Here's the next question, number 46. A 400 volts, 15 kilowatts, 4-pole, 50 Hz Y-connected induction motor has a full load slip of 4%. The output torque of the machine at full load is. So we have our 4 options. Now, let's write down what's given to us. So we have voltage given as 400. We have the power given as 15 kilowatts. We'll call this as PM, power. And we have poles given as 4. And we also have frequency given as 50. And our slip S is given as 4%, which is 0.04. Okay. Now to find out the torque, let's write down the formula. So torque developed. Torque developed, T is equal to the power divided by the angular velocity times 1 minus slip. So this is our formula for torque developed. Now we need to find out what is the angular velocity. So that's our next step. Okay. So let's calculate the angular velocity. Omega S. Now omega S is 2 pi ns by 60. Ns is the synchronous speed. So synchronous speed also we will have to calculate. But since we know the formula for synchronous speed, right? Let me just write that down here for you. We know the formula for synchronous speed as 120 f by p. So let's substitute all of this over here and find out what is the value of omega s. So I'll write that down here. Omega s would be 2 pi 120 f by 60 p. That results in 4 pi f by p. Isn't it? So since 60 goes here 2 times and that's 2 times 2, 4. So that's 4 pi f by p. So you substitute the values over here. 4 into 3.14 into 50 divided by 4. That should give you a value of 157.07. Now this is in radians per second. Okay. So we have our values of omega. We have the value of power. and we also have the slip. So let's substitute those values into the torque developed over here and find out the final answer. So we have torque, which is power divided by omega times 1 minus S. So let's substitute. The power is 15 into 10 to the power 3 divided by omega is 157.07 times 1 minus 0.04, which is the slip, right? Okay. So solving this entire thing, you should get a torque of 99.47 Newton meter. So this is our final answer here. And this matches with 99.47, option C. So for this question, option C is the right answer. So this is the solution, and I hope it has helped. Here's our next question, number 47. For a 1.8 degree two-phase bipolar stepper motor, the stepping rate is 100 steps per second. The rotational speed of the motor in RPM is. So we have to find out the rotations per minute. We have been given 100 steps per second. Okay, so let's begin by writing down what's given and then we'll proceed. Okay, we have our angle theta given as 1.8 degrees. We have also been given that the rate is 100 steps per second. Now let's find out the steps required for one revolution. So steps required for one revolution. That will be 2 pi by theta angle, which is 360 divided by 1.8, and that gives us 200 steps. So here it is 200 steps required for one total revolution. Now let's find out what is the time required for one revolution. Okay, so here time required for one revolution, which would be the number of steps divided by the rate, the stepping rate. So this would be 200 divided by n, which is 100, and that is 2. So the required time for one revolution is 2 seconds. Now next we have to calculate revolution per second. If we calculate what is revolution per second, we can then calculate what is revolution per minute. So that's our next step. Revolution per second would be 1 divided by 2, and that's 0.5. So revolution per second is 0.5. Then what would be the revolutions per minute? 0.5 times 60 seconds, isn't it? So that would be the final step. Okay, so here the final step is revolutions per minute, which is nothing but RPM. And that would be 60 seconds times 0.5 times 0.5. And that gives us 30 RPM. So what we did over here was first calculate the steps required for one revolution, then calculating the time, and then seeing the revolutions per second. Because we have the number of steps, we have the time required for one revolution. So revolution per second, just flip that over, reciprocal of this. So that's 1 by 2, 0.5. Then revolutions per minute would be 0.5 times 60 seconds. So that's 30 RPM, which matches option B. So for this question, the final answer is option B, 30. Well, I hope this has helped.